Reconnect to the Wi-Fi because we're not super plugged. Like honestly, let's see. I don't understand this. I remember we briefly went over like what a manifold is. Like that. Just has a as integer. Yeah, I think it's enough. You just.
All right.
That's yeah.
Yeah. All right. Hello everyone. Welcome to Geometry of Data. Today, first of all, let me do a correction in the previous class. When we were talking about open ray topology, I had defined the topology as such where the topology was the empty set, the real set, and a union of open rays which go from B to infinity, right? For every B element, really, right? So I had missed adding these brackets. So essentially, these two elements are not there individually. It's an open set from B to infinity, right? So if you have that in your notes, sort of fix that. All right. So today what we'll do is that continuing from last class, we had sort of introduced an intuitive idea of what manifolds are. What we'll do today is define manifolds more formally using math, and then sort of take it from there and keep adding more structure until we end up reaching tangent spaces and are able to do calculus on these manifolds, right? So let's just recall what a manifold is again. Right. So, all right. So, a manifold is a topological space. It's from the topology. Tau, which has three basic conditions. The first one is that the space should be a Hausdorff space, right? As you recall from last lecture, what Hausdorff spaces are. That's the first condition for a topological space to be a manifold, that it should be a Hausdorff space. Can anyone quickly sort of define what a Hausdorff space is? Yeah.
All points are separable.
Correct. So intuitively, it's just a space where all the points are separable. There are open walls around all the points so that those open walls do not intersect. So every point sort of has a neighborhood around itself so that it can be separated from other points. So that's the first property of manifold. The second property then is that it should have a countable basis. Right? The basis elements of the space should be countably infinite. They could be still infinite, but should be countable so that each basis function can be mapped to an integer and so on. That's clear, right? So yeah. I have an example of a countable basis versus an uncountable basis. For example, if you consider just very quickly, just so that this is clear to you, let's say there's a topological space X comma tau, which is just the is just induced by the metric space, right? So here the metric it is the space as an induced by metric space. And as you recall, a metric space X comma D is just defined by open walls around each point with small radiuses, right? So if you consider the basis for this, it could be a collection of all open walls around X, such that this X is an element of the data, like all of X, and epsilon is greater than 0. The epsilon is the radius of the ball, right? Now, is this spaces a countable basis? Does anyone have any guesses? Just yes or no? Any guesses? Yeah.
But I can't see.
Oh, right. Yeah. The camera mode. Yeah. Anyone? Any guesses? All right. So as you see, because this is defined for each value on X, this also includes all the rational plus the irrational numbers. So essentially, all the basis depends on the number of X's that you can pick, and because the number of X's here is infinite, this gives you like an infinite basis, which is fine, but it's not even countable because there's always another ball that'll be very close to the ball that you define, because the numbers are very close to each other. Like, because there are infinite number of irrational numbers between any two rational numbers, there will always be an infinitely many open balls. But because you cannot map each of these open balls to an integer, this then becomes an infinitely uncountable basis, right? Does that make sense? All right. So just changing this a little bit will make it countable. And how do we do that is like this. So now let's say you have a space Rn, right? Which has the standard topology. So standard topology means that it has the metric space and the Euclidean topology that we are used to. So this Rn space has the standard, which means Euclidean topology. But now here what we'll do is we define the basis elements as such, like basis confining ball around X, but the X are only rational numbers, right? Yeah, and also, yeah. Right? So now what you'll see is because the X's are only picked from rational numbers and there's countably infinite rational numbers, this base is still infinite. Like this infinitely many elements in this. There's infinitely many elements in this also. But all infinities are not built the same. This one is a smaller infinite than this one, because between any two points there are infinitely many basis elements, but here, because they are mapped only to rational numbers, it still covers the entire space, because you can always find a ball, every rational number in a ball around like a rational number, right? So all the space is still covered, but because we pick rational numbers which are discrete, this becomes countably infinite and gives you a basis which is countable, right? All right, just very quick. Go ahead.
I think epsilon also has to be rational, right?
Yeah, exactly. Yeah,
We
yeah.
don't have uncountable epsilons.
Yes, exactly. So both x and epsilon are then rational numbers, right? Okay. Okay. So those were the first two properties of having a manifold, a topological space which has the Hausdorff properties and also has a countable basis. Right. And the third property then is what we had. Yeah.
Could you quickly define what epsilon is?
Yeah. So in a standard topology, what we define the whole space as is a collection of points and open intervals around these points, which are called b epsilon x, and this epsilon is the radius of the ball.
Oh,
Right. So when we mention epsilon balls, this is what we are sort of referring to, and this epsilon being the radius of the ball around the point. All right. So the third property then is that it should be locally Euclidean of dimension n. Right. Okay, so we'll look at this property a little bit more in detail because we've only seen it through examples last time. Like, for example, like this would not be locally Euclidean because of the crisscross. So now let's see this a little bit more formally. Okay, so let's say we have topological space like a torus, right? And this is defined as x down. And then you have the real line. Sorry, the real plane with the standard topology. N-dimensional real plane with standard topology. And recall that standard topology just means that it's Euclidean and it has the Euclidean distance metric. Right. So now let's imagine that you have a point here with the neighborhood U. And the same point can be mapped here with an arbitrary neighborhood here in the real plane. Right? Is this whole surface directly homomorphic to this topology? Right. That's correct. So because the whole surface is not directly homomorphic to this space, that is very obvious because of the homomorphic definition that this space should be continuously transformable without filling up the holes or making any new holes to this surface, right? So this essentially is not directly homomorphic globally. So this is not globally homomorphic, right? But is it locally homomorphic? That is what we want to check. So local homomorphism means that this neighborhood around you, this neighborhood should in like in a small area around the point x should be homomorphic to the Euclidean space, right? So this we only care about this region being homomorphic to the Euclidean space, right? Okay, so just quick recall that homomorphic if mapped from x to Rn is continuous and bijective, and the inverse is also continuous and exists, then it's considered a homomorphism. So if you can go from this point to this point, you should also be able to come back to the same point, right? So we can see here, like as an intuition, that on any surface like this, which is a two-dimensional surface, if you pick a point and take like a closed neighborhood around it, that would be homeomorphic to the Euclidean space, right? So let's just define this in some words. Okay. So the first definition for today is for this property, right? So X, this topological space, is called locally of dimension n if for all the points x in X, there exists an open neighborhood U in that topology, and also exists a homomorphism H, which maps this U to U prime, and U prime is this area in the Euclidean space, which is the neighborhood of that point, where this U hat is also open. Right? Okay. One thing that you should also note in this definition is this map H U to U is called a chart, right? Because it's like a chart of that surface in the Euclidean plane. So it's sort of like, it's just called a chart, right? So we need to remember this terminology. It's called a chart of your topological space. This. Right. So now, how do we use this property to sort of add a little bit more structure to our manifold? Let's imagine a torus again. Right. And let's say there is a neighborhood U and also an overlapping neighborhood V. Right. And we have a coordinate chart H, which maps this U to the Euclidean plane as U prime. And also another chart K, which maps this other neighborhood V to V prime. And the shaded area is the overlap between these two, right? So there are two different maps. They sort of are mapping two different neighborhoods to the Euclidean plane, but there is some overlap as well. So there are points here which will have the same corresponding points here as well, which are technically the same points. But to add more structure, now what we should be able to do is that go from this chart to this chart using a transition function omega, and we'll see what this transition function is a little bit more in detail. So that you are able to transfer the points to a Euclidean plane and then transfer it to a different neighborhood and then go back to the torus, right? So this is why we need maps, because this is again in Rn and this is also in Rn, right? So the transition map essentially is taking you from Rn to Rn, making it slightly more likely to be differentiable. And once this is differentiable, that kind of property will add a little bit more structure to our manifolds and help us, finally be able to reach a point where we are able to do calculus on these surfaces. right? So before we sort of look at this a little bit more in detail, let's look at one more thing. One more terminology that we'll need later is the notion of an atlas.
Excuse me.
Yeah.
What the W or omega means from the.
Yeah, so this is a transition map. This is called a transition map. Because it sort of helps you to transition from one neighborhood to another neighborhood without being forced to go back to the manifold. Right? You can directly do this from a Euclidean space to a Euclidean space because the mapping takes in this value and gives out that value. Yeah.
Why is the overlap important in this case?
Yeah, because we just want to see if there are overlapping neighborhoods. What we want to be able to do is that we extend the map through the whole manifold. And if you can show that you are able to sort of transfer from one mapping to another mapping, you can sort of extend it to the whole manifold and be able to do calculation throughout the manifold using these overlapping properties. Yeah.
So does each of the locally or have a transition between them?
Yes, so depending on what the neighborhood is and what your manifold is, you will get multiple maps that sort of map these points to the Euclidean space and then use them. So this is just a general example. So there could be infinitely many such neighborhoods, and you can sort of transition between them using yeah.
So it's like U and V have different mapping function.
Yeah.
How does that work? Transitioning from U to V.
Yeah, we'll look at that more in detail with an example also, like in the next few slides, so that will get clearer.
Is the omega function only for the overlapping points or for all the points from?
Yeah, so the transition map is technically essentially only for the overlap, right?
Yeah, it was only defined that so one way to think of this overlapping charts and the transition is analogous to change of variables. If you had two coordinate systems and you want to change variables between, so just think of like Cartesian coordinates, like a rectangular grid, and like polar coordinates in 2D. You need to change coordinates. There's a formula, right? That's a coordinate change. That's one of these transition maps. But now we're going to generalize that concept. And like Aman said, there's infinitely many coordinate systems you can put on a manifold and need these transitions to be able to move between them so that the manifold is still well defined no matter what coordinate system you put on it. And to add the complexity, the coordinate system typically is not going to cover the entire manifold, it's just a patch of the manifold. And that's why this overlap comes, because that's where both coordinate systems are defined only in the overlap. So the transition is only defined in that overlap where they're both the U and the V coordinate system are defined now. But yeah, keeping your analogy in your mind of like, just calculus, you do change coordinate formulas. That's what we're doing on manifolds.
Yep. Any other questions? Okay, so let's move on. So what so we were defining what an atlas is. Okay. So you can already see that such kinds of charts will help us calculate on the manifold in some way, like sort of some transition between coordinates, sort of take one point from one coordinate system to another coordinate system, sort of calculate differences, things like that. So because such chart help us calculate on the manifold, what we want to do is be able to calculate on the whole manifold, right? And this is only for like a specific neighborhood. So what we need is a lot of charts, right? A lot of charts to sort of cover the entire space so that we are able to calculate anywhere on this manifold, right? And that is what the notion of an atlas is. So the definition of an atlas is that it's called a collection of charts UI, HI. Yeah, so remember that the chart is always sort of defined using the neighborhood and the mapping function both, because it needs to have the information of what the neighborhood is, right? Because the chart is only defined for this neighborhood and also what the transition function is. H, right? So if you have infinity, like a lot of such charts, I'm just indexing it using I. So you have a large number of such charts, where I being like some integer capital I is called an atlas. If the union of all of these charts over the values of I is equal to the entire manifold. Right? Right, and this again, remember, this does not have to be countable. So you can have like countably infinite such neighborhoods, as long as the union of all of those neighborhoods sort of give you the entire manifold. That collection of maps is called an atlas, right? Okay, so yeah, so that's just what an atlas is. By definition, if you think about it, every manifold will at least have one atlas, like because of the properties of manifold, it at least have one unique atlas, not unique, one atlas that sort of covers the entire space and is look like sort of mappable to the Euclidean space, right? Because all of the neighborhoods are individually mappable to Euclidean spaces, you can imagine that if you take all of them together, the manifold will have like one atlas at least. Right, so let's look at an example. Yeah, this will make it much clearer. Right, so let's take an example of a sphere, S2 sphere. Which is embedded in 3 dimensions. Like we're only talking about the surface of the sphere, and the sphere is defined as x in 3 dimensions, such that the Euclidean norm of x equal to 1. Right? Yeah, this is the Euclidean norm. It's clear, right? We are just defining a surface of a sphere in the Euclidean. Right? And this is a 2-dimensional manifold because the surface is 2-dimensional, right? It's embedded in 3 dimensions, but the surface itself is 2 dimensions, so 2-dimensional manifold. Okay. So what do we want now is that we want a set of coordinate charts that sort of map this surface onto the Euclidean space, right? So let's start by only looking at the southern hemisphere of the sphere. So essentially, on right? And let's say that the map here is called H, and this will map to, if you can imagine, if you look at this surface from the top and you sort of stretch it onto like a Euclidean coordinate system, you can see that it maps to a circle around you, right? Look at the sphere from the top, just sort of spread it out and become like a projection. The projection will look circular, right? Let's consider that this space that we are sort of mapping is called U3. And I'm calling it 3 because we are sort of dealing with the third index. Like for example, because of the 3-dimensional sphere, you have 3 coordinates, x1, x2, x3. And we sort of generalizing the atlas to sort of cover the whole thing. So right now we're only looking at the third, like the sphere in the 3rd dimension. So we're calling it U3 because x is only like sort of we're losing the information of x3 when we sort of project it up, right? Okay, so this U3 is defined as points x1, x2, x3, which are in 3 dimensions, the Euclidean space, and x3 is less than 0, right? Yeah, so the fluid hemisphere, right? I'm also adding a minus sign here because as you can imagine, if we have like this criteria of x3 greater than 0, we'll cover the upper hemisphere, right? So this minus indicates that we are in the lower hemisphere. If we have a u3 plus, that will be x3 greater than 0, so the upper hemisphere, right? So the coordinate map for this one is then again, like I'm changing the nomenclature, it's called x3 comma minus, right? The corresponding map for the upper hemisphere would be x3 plus. Okay. Now this area is called, let's call this u hash 3 minus, right? This is u prime because this is projected onto a different space. Because this is the same space, I'm calling it u3. And because we're only dealing with the negative hemisphere here, this is for the negative hemisphere, right? So coordinate map for this is you can go from here to here. Now let's define what this is, right? So u3 prime 3 minus will then become equal to x1 prime comma x2 prime in 2 dimensions because that's 2 dimensions, and the Euclidean norm is less than 1, right? This is clear, right? Because we are only want the space, so the norm should be less than 1. So all the points inside the space are sort of u3 minus prime. Okay. All right. So let's define the h3 minus function then. Like, let's see what this map looks like specifically for this example. I'm just writing it here. So h3 minus, not very hard. You can see that what we want is to go from this 3-dimensional x1 comma x2 comma x3 point to 2 dimensions, right? x1 comma x2, and what do you think should the third dimension be?
0.
Yeah, 0. So because it's only 2 dimensions, we don't really write 0 at all because everything will be mapped to 0. So you just drop the third coordinate and it already gives you a map that will map every point here to those points, to inner space. Yeah.
Just to clarify, is that the distance of x equals 0 means the radius is 1?
Oh.
Sorry.
This one?
Yeah.
Yeah, so the radius is 1, like it's a unit sphere. Right? So all the points sort of lie on the surface of the sphere and the radius is 1. Okay. Okay, so this is the forward H3 map. Now we want to see if the inverse map of this also sort of, yeah, so the inverse map also should be defined, and we should be able to figure that out very easily. So here H3 inverse for the same minus property will then be, let's say you have 2 points x1 prime and x2 prime, and these two are points on the R2 projection, the projection of the sphere that you have in 2 dimensions, and to take it to 3 dimensions again will be x1 prime will be the same, x2 prime is the same, and it gets on the 3rd dimension. Not 1, because what you want is that you want to recover this hemispherical structure. So there should be like different values for each z, so that you map the whole surface of the bottom hemisphere of the sphere. Right? But we know 2 coordinates. How do you figure out the 3rd coordinate?
3.
Square root of x1.
Yeah, correct. So what you just do is that you take the square root of 1 minus the norm of this point, which is that, right? You take the norm of x prime, subtract it from 1, and because we're dealing with the negative hemisphere here, there's a minus sign here, because we want to fill up the negative axis. right? So you can see that we are able to sort of get a forward map that goes from your manifold to the Euclidean space, and also a reverse map that goes from the Euclidean space to your manifold, right? So now, is this already an atlas? Anyone?
Not right.
Yeah, so because it's only covering half the space, it's not essentially an address yet. But let's say we sort of generalize the whole thing, we sort of instead of this minus have a plus as well. And we have like two maps for the upper hemisphere and for the bottom hemisphere. U3 from H3 plus minus both, and yeah, sorry, U3 plus, H3 plus, and U3 minus, and H3 minus. Is this now an atlas? Any guesses? Well, so if you think about it, it's the lower hemisphere is taking everything below the equator. The upper hemisphere is taking everything above the equator. So there's points on the equator which are still missing that you don't really have a mapping for. So this still does not cover the entire manifold, essentially. So it's not an atlas yet. But what do we need to do to sort of generalize this and add more, charts to this to make it an atlas? Yeah.
Can we just make it close and then we include the equators then?
So by definition, all of these maps are sort of supposed to map from an open interval to an open interval. Yeah, so you can't really make one of these closed to include the equator. Any other ideas? Yeah.
You can take a small neighborhood like a circle along the on two edges of plus minus two sides of the equator and cover the entire sphere.
Yeah, so what you're suggesting is that we take like a chart which is only defined in the neighborhood of the equator and sort of map that to like a equivalent Euclidean space and sort of use that to complete this like cover the entire manifold. And that seems like a reasonable thing to do. And yeah, that would also give you essentially an atlas which sort of covers everything. But the easiest, most general way to do this is that if you sort of generalize this to all dimensions, we are only dealing with the third dimension of it. If you sort of generalize this to all dimensions, what will happen is that for the sphere, the third dimension will cover the bottom hemisphere and the upper hemisphere, right? So only the equator is left, right? And now if you do like say U2 plus comma H2 plus, that will cover this hemisphere, right? And if you do the opposite, that will cover this hemisphere. Now, all of the equators are already taken care of, but still there are some points which, yeah, so you can then generalize this to U1 as well and sort of take this hemisphere and that hemisphere. And that will essentially sort of generalize this formulation for the entire space. And that gives you like an atlas. So formally, I can rub this, right? Anyone still? Overall, for this space, the collection U I comma plus comma minus and HI comma plus comma minus for all I in an element of 1, 2, 3 gives you right? That makes sense. We have just generalized the formulation that we saw for the lower hemisphere to the upper hemisphere as well as like hemispheres like this and also in the third dimension. So this will give you an atlas because it will cover the entire space and map essentially every point to the Euclidean space using the mapping function. Right, so that's an example of what an atlas is and how you can find this atlases to sort of cover the entire space. Now, let's add a little bit more structure to these manifolds to sort of be able to finally do calculus, which we've been wanting to do since the first class. Okay, so I'm drawing the overlap diagram again because it will be used in this example. H, which maps this to Euclidean space, this, and let's say this is the overlap. It's new prime and K. Yeah. Okay, so essentially this area, if you think about it, what would this area be called? It's essentially just the intersection of U and V. So U intersection with V, and then that is applied over with the function h, right? So this intersection, if you apply the function h on it, will give you this region, right? Makes sense? The same thing here, the function k, if applied on the same intersection U intersection V, will give you this area, right? Now, our omega, which is a transition map from this region to this region only, is, as you can see, is going from Rn to Rn again. And this omega is a transition map between this region and this region. And we already sort of know how to deal with such transition maps because both the domain and the range are real Euclidean spaces like that we are used to already. But we want this omega to have like a certain set of properties for this to sort of extend into a place where differential calculus is possible on the manifold. So what we want essentially is we'll introduce another technical terminology which will impose 3 more conditions on our transition function to add a little bit more structure. Okay, so what we want is that we want this transition map omega to be a CK diffeomorphism. New terminology, we'll look at what this means after this. Right, so what does CK diffeomorphism means? So it has, so for omega to be CK diffeomorphism, it needs to sort of satisfy the following criteria. First one, that omega is K times differentiable. What does this mean? This means that the partial derivatives up to the kth order should exist for this transition function omega, right? This simply means that it should be differentiable k times and should not exist in those differentiations, right? And this can also be written in math as such. We want omega to be a C K diffeomorphism and acting on the like what it's acting on, and here we see that it's acting on H U intersection V, right? Okay. Second property is that omega should be bijective. And why do we need it to be bijective? Because what we want to do is that we want to be able to go from one map to another and also be able to come back from that map to the inverse, like also have the inverse exist so that we can sort of transition between maps in the forward and the backward direction. And for that to happen, you should have the omega should be bijective. And also the third property that omega inverse is also k times differentiable, which means G segment. Oh. Yeah, note that this k is not the same as this k. This k is this function. Let's call it k star so that no confusion. Right? So given these three properties, if your transition maps sort of satisfy all of these three, then you can say that your transition map is a CK diffeomorphism. If it's infinite times differentiable, then it's called C infinite diffeomorphism. And you can sometimes say it's just a smooth diffeomorphism or just a diffeomorphism is sort of means that it's C infinite, right?
What does K depend
Well,
on?
it depends on what your transition function is. Some transition functions will only be differentiable once and then not exist after that. So in that case, K will be equal to 1. And you'll then sort of specify the omega function to be C1 diffeomorphism. Or if it's differentiable twice, then you can say that it's the C2 diffeomorphism. Okay. Now note that just as an example of this, that C0 means that it's 0 times differentiable, which only means that it's only continuous, right? So C0 means that it is only continuous. C1 means that it's continuous and it's differentiable 1 times. C infinity means that it's continuous and also it's differentiable infinite times, which means that all of its partial derivatives and all derivatives of any order exist for that function. And that is what we would want to be the ideal scenario. And that is what is called as smooth map. It's when C infinite, which means differentiable and continuous. Correct? Okay. Right, it's just a definition. Any questions up till here? Yeah.
So what does that smooth is that? Smooth is that is for the omega function?
Yeah. So the smooth is sort of referring to the omega function, but you'll see the smooth come up several times. Whenever like a manifold is completely differentiable, it's infinite differentiable, you say there's a smooth manifold. You can say that a function is continuous and infinitely differentiable. You can say that it's a smooth map. So this terminology is sort of directly related to it being all the partial derivatives exist. Yes.
So you said W belongs to C to the power of K, what does that?
Yeah, so this is just a terminology which says the same thing as this, right? So if you want to say that omega is K times differentiable, this is how you just write it in math. That it's an element of all the CK functions, which means all the CK functions are K times differentiable functions, and omega is a part of that.
So W actually only take the intersections of these two maps.
Correct.
It does not include anything that's outside of the intersection.
Yeah.
So a constant mapping is a smooth mapping?
What do you mean, a constant? Like an identity map?
Just constant, just mapping a point to one point.
Um,
Mapping any point to one point.
Like mapping all the points to one point,
Yeah.
then that sort of does not satisfy the definition at all.
So I think you're asking, is it smooth? The answer is yes.
Yeah,
But it's
but
not.
it's not a
differential.
secret.
So, yeah, so smooth is, yeah, different different gotta be, both directions have to be smooth and bijected. There you go.
All right, so okay, yes. Another terminology that we need to define quickly so that we can use it later is that this is a property that we need to remember is that two charts uh, two charts H and K are differentiably compatible if the map omega between them is differentiable. Right? So we just say that two maps, H and K, are differentiable compatible if the map between them, the omega, is a differentiable function. That's it. This thing can also be written as such on two charts, H and K, are called C, K, U, V, compatible. If omega is CK determinant. Yeah, just some terminology so that if later you encounter that omega is a CK diffeomorphism, or let's say two charts are given and they are CK smoothly compatible, this is what that means essentially. Right, so now you can see that for any manifold there can be a lot of atlases which sort of cover its the whole thing. So it's not necessary that every manifold sort of has only one atlas, but we also need a notion of a maximal atlas. Right, a maximal atlas, a maximal CK atlas, sorry. So an atlas A is a maximal CK atlas if number one, yeah, first of all, A is just a CK atlas. This just means that it's a CK atlas, and for it to be maximal, then it should be it should cover like the entire space, right? So for any other CK atlas, let's say like it should be maximal, which means essentially is that if there exists any other atlas B, and B is also a CK atlas, for instance. B should not be a superset of A. Right? That's all it means. Like if you're able to come up with another atlas which has something missing from this atlas, then this is not a maximal atlas. It needs to have everything that it needs to sort of cover the entire space and be completely maximal. Right? So we have sort of studied several properties. Now put them all together to sort of finally define what a differentiable manifold is. A differentiable manifold only has needs two of these properties that we saw. The first one, it should be an n-dimensional topological manifold, of course. And two, that should have a maximal CK atlas. Right? So because the differential manifold only sort of have these two, it's also called that the manifold has a CK smooth structure. Both of them mean the same thing. So we sort of defined all of these things, like what an atlas is, what a CK atlas is, what a C-infinite atlas is, to be able to define a differentiable manifold using these two properties. Should be an n-dimensional topological manifold and should have like a maximal CK atlas. As long as these two properties are satisfied for any manifold, you can know that it's a differentiable manifold. Let's look at some examples now.
Sorry,
Yes,
could you please say again what does maximal refer in
Yes.
this context?
correct. So a maximal atlas is just an atlas which sort of covers the entire manifold, right? It should not leave out any points. It's a collection of maps. If it's able to cover the entire manifold, every point on that manifold is considered a maximal atlas.
Okay, and what if there is another atlas that or all the points?
Yes, so there
It's
are
also maximum.
so the definition only suggests that there is at least one maximal atlas for a manifold, but there can be multiple atlases. Yeah. But if you can pick one of those, which is a maximal CK atlas, and then use that, then sort of you can define a differentiable manifold unit using that atlas.
Thank you.
All right. Okay, so we have already seen the sphere example a couple times, but now let's look at it in the general sense where we are able to look at an SN sphere, which is an n-dimensional spherical surface in a d plus one dimensional Euclidean space. N plus one, sorry, n plus one dimension Euclidean space. It's right. So any n-dimensional sphere is always embedded in like one extra dimension in the real on the real Euclidean plane. So yeah. So we need to show that the collection U I plus minus and H I plus minus where I one, two, plus one is C-infinite atlas. Right? For it to be a valid manifold, differentiable manifold. Okay. Now, just recall quickly that UI is Right, and depending on whether it's plus or minus, we can choose the plus minus sign there. Right, and the corresponding map H I comma plus minus is just goes from x1, x2, xn plus 1 to you write x1, x2 up to xi minus 1, and then we skip the ith coordinate because we're projecting it to like a space which is has one less dimension, and I plus 1 up to x equals. Right, this is the general form of what we wrote for a two-dimensional sphere. Now we need transition maps, right? Okay. So omega in this case is okay, let me draw pictures of that so easier. Right, so we're looking at two of these, and the first one sort of maps to so the upper hemisphere is projected to the space. Yeah, the origin is in the middle. I'm just just want to show that, and the overlap is in this part, right? So half of that, and this is what your HI would look like, and let's say there's an HJ, which is a transition. Okay. Right, and you have an omega from here to here. Right. Okay, so let's look at like a specific case of this and sort of define the transition map for that. So what will happen is that once we sort of define transition map for Sn, you'll see that it's differentiable, and that sort of shows that this Sn is an example of a differentiable manifold. Right, so very quickly, let's say for n equal to 2, I equal to 3, and j equal to 1. I and j are just indexing which part of this we are sort of looking at. So j, we just setting arbitrarily j equal to 1 and n equal to 2, and c for this case, because this generalizes for everything. You can sort of change these indexes and sort of generalizes for everything. So here what you'll see is that x hat in that plane has only two coordinates. Yep. Because x prime 1 and x prime 2, and when we apply the h inverse function to it in positive domain, you will get, and why are we applying the h inverse function? Because x, let's say, is a point here. What we want to do is go back to this manifold, project it back to here, and then sort of use omega as this point to that point, because we can't directly go from here. What we do is we project it back to the manifold, then we project it back to this space, and then use that as our omega, right? Because essentially what we want to do is that go from this point to that point. So because there's no direct way to do that, you go through the manifold, because you have these inverse functions also sort of defined by definition, right? So the inverse function will give you x1 prime, x2 prime, and like we saw before, the third one is just b1 minus x prime, right? And then you apply the other function, the j function in the positive direction, and that will give you, that will again further drop one more coordinate from this. And which coordinate will we drop? Because j equal to 1, we'll drop the first coordinate completely, and then this will be x2 prime and root of 1. Right? So you can see that you can sort of define, and this is just the omega function, right? And omega function written simply is just a combination of your h j function in the positive with your hi functions inverse in the positive. Right? Because given a point here, you first need to apply the hi inverse to go back there. This is hi inverse. And then you apply hj again to go back here. So this omega is sort of defined like this. Right? Understood? Okay. So because we can see that this is differentiable in both directions and satisfy all the general conditions for an Sn sphere, not just an S2 sphere. So we can see that Sn is a differentiable manifold. Right? Okay. All right. So now let's look at one more concept, which is called smooth maps. Then we'll look at tangent spaces, two more concepts actually, and then smooth. So let's say inverse. And there's a function f which takes points from this torus and sort of takes them to another manifold, which is a sphere. And both of these are manifold M and N, right? And again, like we did before, let's find neighboring areas here, neighboring areas here. And sort of project everything back to the Euclidean space using the respective maps. So use H, U, V, W. U. Notice the change in notation here. This is not called K anymore. We're calling it H with a tilde on it. And those two mapping functions will be called K. So an overlap here, that will be prime. Right? Same thing with this. Right? Now we know that we have transition maps between this and this, and also between this and this. And but what if we want to go from this manifold to that manifold? Directly, we can't do these computations directly on a manifold. What we want to do is that through these maps, figure out a way of sort of projecting points from one space to another space. And this can be done through the maps because all of these maps are in Euclidean space, right? So you can map points from that manifold to the Euclidean space, and you can map points from this manifold to the Euclidean space. So somehow what we want to do is that be able to use the properties in the Euclidean space to sort of transition from this manifold to that manifold, right? Okay. All right, so how do we do this? Let's say we want to go from here directly to here, right? Let's say you have a point over here. Okay, any ideas using all of these maps or the functions? Any ideas of how we would project a point over here to a point to a corresponding point over here? Maybe it's outside the. Yeah, any guesses? It's very similar to how we were transitioning from here to here using these K maps. You go back to the manifold and then use the function and sort of project it back to the manifold. So any similar sort of mechanism here, because these two are also connected using the step function, if you notice.
So
Yeah.
through H minus one,
Yes,
then through,
yes,
and then through K.
perfect. Yes. So this is exactly how you transition. What you do is that you take a point here, you apply the H inverse function, which goes in the opposite direction of H, projects the point here. Then you use the F function to sort of project it here. Then you use the K function to come here, right? And now we can again see that this is also from Rn to Rn. And similarly, what you can then do is sort of define a similar transition map from here to here as well. Anyone want to take a guess on what this one is?
Same thing, right? So, which is inverse.
Yeah.
Then take F and then take Q.
Yes. Yeah. Right. So similarly, you can do this, in any direction, things like that. But yeah, so now we want to see if these transition maps are differentiable or not, right? So what we want to do is that to be able to tell if F is a differentiable map from here to here, what we do is that we sort of look at these maps, which are proxies of F in through the Euclidean space, and see if these are completely differentiable or not differentiable. And is there another thing is that because this F function sort of can be written through multiple ways of these, what will happen is that if one of them is sort of differentiable, if you find any of these transition maps to be differentiable, it does not matter what other formulation you write it into, all of them will be differentiable, right? Okay, so now with this in mind, let's write the definition. Okay. So the definition is that let M and N into be C infinite smooth structures. And this is given, right? Smooth manifold. That both of these, as we saw that the sphere was a C infinite smooth manifold just right before this. You can also sort of see that the torus is also a C infinite smooth manifold. So given two C infinite smooth manifolds, a map F which goes from M to N is called T times differentiable. And please note that this differentiability is only defined as a point. There's no meaning of a function being differentiable everywhere. It's just, is it differentiable at the point of definition or not? So is a k time differentiable at P, which is in M, if for charts U, H, W, K, with P being in U, change with this point. this point is in U. And the function, when you apply the function to P, that value is also in U, which means that the image of this function is over here. Right? This is C k times differentiable if the map K, like we have times H inverse is A times differentiable. And right, so that's just a definition that we sort of built up using all of this.
So when we did the transitioning from like the U prime to W prime, right?
Yes.
Like, we didn't need to use any omega function.
No, so here, this is also like a transition map which between two different manifolds, but yeah, so this does not really use omega at all because you don't really want to go from this neighborhood to this neighborhood at all. What we want to do is that take this point, sort of project it back to this to this point in the manifold, and then use the f function to come here, and then use the reverse map to come here. So it's essentially sort of bypass all of that, but via only using the maps. And this is also a composition of maps only, essentially. So
So for the k times differentiable map, it doesn't matter what the point is. It doesn't have to be in the overlap.
it does have to be, yeah, it does have to be in the overlap. So these are the conditions that it needs to follow. That P should be in U, and f of P should be in omega. Right? So
You could delete the omegas in this picture.
yeah, exactly. It won't matter.
Right, they aren't needed for the definition here. I think it's the main confusion question. There is an overlap that, with P's and U, you then map it over to N. For this definition, you need to find a chart W, which is, it means F of P needs to hit the W chart. And this has to hold for any chart where P's in, and any chart in where F of P is in. It's kind of like for all charts that satisfy these conditions, this has to hold.
And then why are V and Y relevant in this two definitions?
We don't actually need them for this definition. I think the point Aman was making was that if you did change coordinates, because that's a differential function, it's just a you compose.
Yeah.
You get another differential, this would still hold.
Yeah, we were trying to.
It's just a change of coordinates, but everything.
Yeah, so once you sort of establish that one of these function transition maps between one manifold and another manifold is differentiable, you can sort of change the coordinate system and then do the same thing via another coordinate map like H tilde stuff, and that would also sort of be differential. Yeah, so that was the overall point in drawing the rest of it. Yeah, we can end the class here, but yeah, any other questions?
We'll pick back up with this on Thursday, right, at this point, yeah.
No? All right. Thank you, everyone.